As a man building the most powerful rocket ever, you would expect Elon Musk to be always gazing upward. However, the billionaire genius is also interested in what goes on underwater and with the most unlikely ally, the Russians. Stay tuned as we bring you the terrifying underwater Russian discovery just made by Elon Musk. Lake Baikal is a natural beauty that draws visitors from all over the world. It is the world's largest and deepest freshwater lake, holding an unbelievable 23% of the world's fresh surface water. It is also one of the world's oldest lakes, dating back 25 to 30 million years. Lake Baikal is located in southern Siberia between the Republic of Buryatia and the Irkutsk Oblast and has an area somewhat larger than Belgium with 31,722 square kilometers or 12,248 square miles. It runs 636 kilometers or 395 miles from north to south, and its widest point is 79 kilometers or 49 miles. Its coastline stretches for around 2,100 kilometers or 1,300 miles and includes sandy beaches as well as rocky cliffs. The lake contains 27 islands, the largest of which are Olkhon and Bolshoy Ushkani. Lake Baikal is what scientists call a rift lake, meaning it was produced by the Earth's crust separating along a fault line known as the Baikal Rift Zone. However, this zone is still active, triggering earthquakes and volcanic activity in the surrounding area. In addition, the lake is growing by roughly 2 centimeters or 0.8 inches per year, making it wider and deeper with time. The lake's maximum depth is 1,642 meters or 5,387 feet, or to use more fancy terms, 898 fathoms, making it the world's deepest lake. This means the lake's bottom lies more than a mile below sea level and contains several underwater features such as slopes, ridges, and canyons. Lake Baikal's hydrology is complex, with over 330 rivers and streams coming into it and only one outlet, the Angara River. The Selenga River is the greatest tributary, draining a huge basin in Mongolia and Russia. Human settlements and culture have existed on Lake Baikal from ancient times. The Buryats are the region's indigenous population who practice Buddhism and shamanism and have a profound attachment to the lake as a sacred spot. Kurbat Ivanov was the first Russian adventurer to reach Lake Baikal in 1643. Since then, the lake has served as a hub for commerce, exploration, research, and tourism. The lake was designated a UNESCO World Heritage Site in 1996, recognizing its exceptional ecological and cultural value. However, Lake Baikal has been a source of fascination for scientists, leading to many intriguing discoveries. One of them has to do with ghost particles, also known as neutrinos. Neutrinos have a lot of promise as they will be useful for many things, which is why a progressive mind like Elon Musk would be interested in them. For example, Elon Musk has often mused about the possibility of the existence of extraterrestrial civilizations. Scientists have discovered that aliens could use beams of neutrinos to modify stars for interstellar signaling. The idea is that highly advanced extraterrestrial civilizations may manipulate pulsating Cepheid variable stars with extremely high-intensity neutrino beams in order to communicate information across the cosmos. The theory explains that aliens might use pulsed neutrino beams to change the pulsation period of a Cepheid variable star. Such neutrino beams might produce a binary signal from the star consisting of a normal pulsation period paired with a neutrino-triggered, artificially shorter period. Cepheids are a natural choice here because they can be seen from enormous distances, and any emerging technological society such as ours would presumably see them as distance markers. The next step of the research is to search these variable stars for patterns that indicate intelligent signals. Musk has also been asked his views on nuclear energy, and amazingly, neutrinos can help in this regard. Scientists can use neutrinos to catch countries that violate nuclear non-proliferation treaties. The United Nations nuclear inspectors are not always granted immediate access to a country's nuclear reactors, which can also be used to produce weapons-grade uranium. However, the neutrino could provide a workaround for on-site examinations. The Water Cherenkov Monitor for Anti-Neutrinos, or Watchman, is the first neutrino detector designed exclusively to demonstrate technologies for remotely monitoring plutonium production in reactors, according to the scientists. Watchman will test the theory next year from 1,000 meters below ground inside northern England's Boulby salt mine, hunting for neutrinos coming from the Hartlepool nuclear power station, which is 25 kilometers away. And much research work is going on about neutrinos in Lake Baikal, where scientists use a special kind of telescope. This is the largest telescope of its kind in the northern hemisphere, designed to study black holes, distant galaxies, and the remains of exploding stars. It accomplishes this by looking for neutrinos, cosmic particles so small that trillions pass through each of us every second. Scientists believe that if we could learn to understand the information they contain, we could map the cosmos and its past in ways we cannot yet fully comprehend. This new Russian initiative will be an important supplement to the work of IceCube, the world's largest neutrino telescope, a $279 million American-led project encompassing nearly a quarter of a cubic mile of ice in Antarctica. IceCube detected a neutrino in 2017 using a grid of light detectors identical to the Baikal telescope, which scientists claimed probably emanated from a supermassive black hole. It was the first time scientists had discovered a source of cosmic rays, a milestone for neutrino astronomy, a science that's still in its infancy. Practitioners in the field believe that when they learn to read the universe with neutrinos, they will make fresh and unexpected discoveries, just as the lens makers who invented the telescope could not have predicted that Galileo would later use it to discover Jupiter's moons. Early studies by Soviet scientists inspired Dr. Halzen to develop a neutrino detector in Antarctic ice in the 1980s. And Dr. Halzen now claims that his team believes it's discovered 2 additional sources of neutrinos arriving from outer space, but this is difficult to confirm because no one else has observed them. He expects that will change, though, when the work of the Baikal telescope increases in the coming years. Despite the Cold War, Americans and Soviets collaborated in the 1970s to plan the first deep-ocean neutrino detector off the coast of Hawaii. However, the Soviet Union was thrown out of the project after it invaded Afghanistan. And so, led by Dr. Domogatsky, the Institute for Nuclear Research in Moscow launched its own neutrino telescope project in 1980. Although it was nearly 2,500 kilometers distant, the obvious location to try was Baikal. The project did not progress far beyond planning and design before the Soviet Union fell, causing many of the country's scientists to become impoverished in their attempts to fall apart. However, an institute out of Berlin joined the Baikal project and was soon absorbed into Germany's DAISY Particle Research Center. The German team's leader, Christian Spearing, recalls shipping hundreds of pounds of butter, sugar, coffee, and sausage to sustain the annual winter forays onto the Baikal ice. He also took thousands of dollars to Moscow to boost the Russians' meager wages. And Dr. Domogatsky and his colleagues persevered. Dr. Spearing recounts that when a Lithuanian electronics manufacturer refused to accept rubles as payment, one of the physicists arranged to pay with a railway car full of cedar wood. And by the mid-1990s, the Russian team had identified atmospheric neutrinos, those caused by collisions in the Earth's atmosphere, but not those from outer space. That would necessitate a larger detector. As Russia began to reinvest in science under President Vladimir V. Putin in the 2000s, Dr. Domogatsky was able to acquire more than $30 million in financing to build a new Baikal telescope the size of IceCube. The lake is up to a mile deep, with some of the world's cleanest fresh water, and a Tsarist-era railway neatly borders the southern side. Most importantly, though, in the winter, it's covered by a 3-foot thick sheet of ice, ideal for building an underwater photomultiplier array. Construction began in 2015 on the first phase, which includes 2,304 light-detecting orbs floating in the depths. The spheres stay hung in the water all year, looking for neutrinos and transmitting data to the scientists' lakeside station via an underwater cable. The Baikal telescope stares down through the entire world, out the other side, into the center of our galaxy and beyond, effectively acting as a big sieve. Larger particles that hit the other side of the planet eventually smash with atoms. However, practically all neutrinos, 100 billion of which pass through your fingertip every second, travel in a straight line. However, when a neutrino collides with an atomic nucleus in water, it generates a cone of blue light known as Cherenkov radiation. Dr. Domagatsky's former colleague down the hall at his institute in Moscow, Soviet physicist Pavel A. Cherenkov, discovered the effect. Many scientists believe that if you spend years monitoring a billion tons of deep water for unimaginably tiny flashes of Cherenkov light, you would ultimately find neutrinos that can be traced back to cosmic conflagrations that emitted them billions of light years away. And this blue cone's orientation even shows the precise direction of the neutrinos that generated them. And it's because neutrinos lack an electrical charge they are unaffected by interstellar and intergalactic magnetic fields and other factors that disrupt the pathways of other types of cosmic particles like protons and electrons. Neutrinos travel as far as Einstein's gravity will allow them to. That is why neutrinos are so useful in studying the universe's earliest, most remote, and most violent events. They may also assist in explaining what occurs when stars far more massive than the Sun collide into a super-dense ball of neutrons 12 kilometers across, producing vast amounts of neutrinos. The Baikal telescope analyzes the southern hemisphere sky since it virtually sees through the Earth. This makes it a complement to IceCube in Antarctica as well as an earlier stage European initiative in the Mediterranean. The team is already exchanging data with other neutrino hunters, and they have discovered evidence that supports IceCube's conclusions concerning neutrinos arriving from space. Now, another massive discovery that has confounded scientists to this day on Lake Baikal is the presence of huge ice rings. The overall shape of an ice ring is difficult to distinguish from the ground. They're huge enough that their ring-like shape can only be observed from planes and satellites. The interiors of the rings are bright, but the outer perimeters are dark where the ice is thin. According to the new research, the rings are about 5 to 7 kilometers or 3 to 4 miles in diameter, with the darker outer perimeter being about 1 kilometer or 0.6 miles broad. During the Siberian winter, the rings can endure for anywhere from a few days to several months. Ice rings like this appear to be unique to Lake Baikal and its neighboring Mongolian lake, Lake Hovsgol, as well as Lake Teletskoy, a Russian lake some 830 miles west of Baikal. However, it is absolutely feasible that they occur in other lakes and have yet to be discovered. Their appearance is unpredictable both in terms of time and location. The ice rings have been linked to a variety of reasons, including meteorological or biological influences, complex hoaxes, and even alien activity. According to one popular idea, the ice rings grow as a result of escaping gas, specifically methane, which surges up from the lake's bottom. However, the rings have been detected in shallow areas of the lake where gas leaks seem implausible. The authors of the new study, a combined team from France, Russia, and Mongolia, organized field missions to Lake Baikal during 2 winters and analyzed thermal infrared satellite imagery of the ice ring to solve the enigma. The researchers bore holes near the ice rings and dropped sensors capable of measuring water temperature at depths of up to 200 meters or 660 feet. Every winter, measurements were taken twice, first in February and again in March. This proved to be risky work. On one expedition, the ice layer beneath their van began to disintegrate, necessitating the driver and passengers to be rescued. Just 2 days later, it happened again. Another group of researchers known as the Fellowship of the Ice Rings discovered an eddy where water travels in a circular pattern at a depth of 45 meters or 148 feet beneath an ice ring. This discovery gave researchers an up-close look at the ice conditions at the late stage of ice ring formation. The water in the eddy was discovered to be 1 to 2 degrees Celsius or 1.8 to 3.6 degrees Fahrenheit warmer than the water around it, and the eddy took around 3 days to rotate completely. The crew discovered another eddy a year later, which had migrated 6 kilometers or 3.7 miles from its original location by the end of March. There was no ice ring visible above the eddy, most likely because not enough time had passed for one to form. A similar phenomenon was observed again when a ring migrated 9 kilometers or 5.5 miles from its starting point. The researchers believe the heated eddies are the primary source of the ice rings based on their observations. Their field surveys show that there are warm eddies that circulate in a clockwise direction under the ice cover before and during ice ring manifestation. The ice does not melt in the eddy center despite the fact that the water is warm because the currents are weak. However, at the eddy boundary, the currents are stronger and the warmer water causes rapid melting. According to the latest research, ice ring formation begins in September before the lake freezes. Wind-churned outflows of water from Bargazon Bay to the lake's center portion create the eddies. The experts believe a similar mechanism is taking place in other lakes where ice rings form. More research is needed to completely understand the cause of these ice rings, but this latest discovery provides a fascinating explanation. However, many puzzles remain, such as why the eddies have a convex shape, a feature found in ocean eddies but not in lakes. And future studies will also have to take the structure of the coastline into account, as it appears to play an essential role in influencing how the eddies flow.